Hey guys, we're going to start our unit on covalent bonding here today. We'll talk about two things in this video. First, we'll just compare and contrast ionic and covalent bonds, see how they're different and how they're similar. And then we're going to get into writing Lewis dot structures for covalent bonds. So first, let's start off by talking about how ionic compounds are different from covalent compounds. We talked about ionic compounds in the last unit, and we learned that they consist of metals transferring electrons to nonmetals. We learned that these were very strong bonds, which means they have high melting and boiling points, and they're typically solids at room temperature. Think about table salt, ionic compound. How do they compare to covalent compounds? Well, they're very different. Covalent compounds are nothing but nonmetals. Nonmetals sharing electrons with other nonmetals. That's the biggest difference between ionic and covalent. These bonds are typically less strong than ionic compounds. They have lower melting points and boiling points, and they're typically liquids or gases at room temperature. Okay, so let's start off by writing some Lewis dot structures here. Let's start off with something simple. Water. Here's how this game is played. There's a couple steps. So the first step is counting up all the valence electrons. We need to know how many total valence electrons there are in this compound. So let's start off by realizing we have two hydrogens. Each hydrogen has one valence electron. 2 times 1 is 2. So of the two hydrogens, there is a total of 2 valence electrons. Let's look at oxygen. Oxygen, there's only one oxygen. Oxygen has 6 valence electrons. 6 times 1 is 6. And then we add up these numbers here. So we have a total of 8 valence electrons in water. Valence electrons. Okay, so that's step one. We have to use all 8 of these electrons. When we're doing these covalent compounds, this is the key. We have 8 of them. We have to use all 8 because remember, this is about sharing. Step number 2, we're going to put one atom in the middle. It's typically the one that's alone because we're only doing simple compounds here. So there's only one oxygen. Let's put that in the middle. Then we're going to put the other elements on the sides. Let's just try to be symmetrical. I'll put one on that side, one on this side. And then we're going to hook them up to the central atom with a bond. Now, this bond consists of 2 electrons, one from oxygen, one from the oxygen, and then one from the hydrogen. One from the hydrogen. So these lines in between the elements represent a single bond. It contains 2 electrons. Each single bond contains 2 electrons. Okay, so how many do we use up here? 1, 2, 3, 4. We use 4 total. We have to use 8. So what are we going to do? We're going to put them around the oxygens. 1, 2, 3, 4. So we used up all 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's part of this game. That's the start. And now the last part is it has to satisfy the octet rule, meaning all elements have to share 8 electrons. The only exception to this is hydrogen. Hydrogen only shares 2, not 8. Remember, hydrogen only has the 1s level. All right, and the most we can fit inside a 1s level are 2 electrons. So there's the 2. Here's hydrogen, 1, 2. Here's the other hydrogen, 1, 2. Both these electrons count for the hydrogen. Both these electrons also count for the oxygen. So each of the hydrogens have 2 that they're sharing. Let's look at the oxygen. 1, 2, 3, 4, 5, 6, 7, 8. The oxygen is technically sharing all these electrons here, satisfying the octet rule. Okay, so we have electrons that are involved with bonding. We can also have electrons that are not involved with bonding. These guys right here These are called unshared electrons or unshared pairs. There's another set up here of unshared pairs. Okay, let's check out another example here. Here's NH3. This is ammonia. So we have to start off by counting up all the valence electrons. So we have one nitrogen, right? Nitrogen has 5 valence electrons. 1 times 5 is 5. Then we have 3 hydrogens. Hydrogen has 1 valence electron. 5 plus 3 is 8. So we have 8 total again that we have to use up. Okay, these represent valence electrons. All right, so step 2. Let's put the atom that's alone in the middle. Nitrogen, it's all by itself, so we'll put it in the middle, and then the hydrogens are going to go around it as symmetrically as you can put them. Really, it's not really that important at this point. Just get them in there. All right. Now we always want to attach these to the central atom. So here we go. There is a bond. There's a bond. There's a bond. All our hydrogens are attached to make this molecule. This is a molecule now. And remember, each of these lines represent 2 electrons. One from the nitrogen and then one from the hydrogens. Okay. So now let's see how many we used up. 2, 4, 6. We used up 6. We have to use all 8. We have to use them all. So let's get them in there. We can't put them on the hydrogens because hydrogens only share 2 electrons. Remember, they're really small. They don't share 8. That's the only exception. Everything shares 8 except for hydrogen. So if these are already sharing 2, remember, here's 1, here's 2. That technically belongs to the hydrogen. So we can't put the extra electrons on the hydrogens. We're going to put them on the nitrogen. Because look, the nitrogen is sharing 6. 1, 2, 3, 4, 5, 6. And now with these 2 unshared pairs, that makes 8. We used up all electrons and they satisfy the octet rule. All these here technically are being shared by nitrogen. That's 8. And the hydrogens are each sharing 2. We're done. All right, let's try another example here. Let's look at carbon dioxide, CO2. We all have heard about that. So we have 1 carbon. Let's get a count of all our valence electrons. 1 times 4 is 4. We have 2 oxygens, right? Oxygens have 6 valence electrons. So that's 12. 12 plus 4 is 16. So we have 16 total that we have to use up. All right, that's our first step. Now let's get this structure built here. Let's put the 1 in the middle, carbons by itself, and let's put the oxygen symmetrically. Let's just put them around like this. And we always just want to attach it one time to the central atom. So now we used up 4 electrons. 1, 2, 3, 4. We have to use 16. So we have 12 more that we have to put in there. So let's just put them in as unshared pairs right now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 total that we needed. Just get them in there for now. It doesn't matter where you put them at this point. We just have to show that they're there. And now we have to check to see if each atom is going to have its octet satisfied. Remember, everything has to have 8. There's no hydrogens here, so each of these have to share 8. So let's look at this oxygen here first. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen's good. How about this carbon? 1, 2. Remember, this bond counts for both the oxygen and the carbon because they're sharing. So 1, 2 for the carbon, 3, 4, 5, 6. That's not enough, so we're going to have to fix that. Let's look at this oxygen. 1, 2, 3, 4, 5, 6. Also not enough. So what are we going to do? The only thing we can do is start moving electrons around to satisfy the octets. So here's one way to do this. We're going to get rid of a couple of these here. How about these 2 here? We're just going to take them out and we're going to move them and create another bond. We're just going to move them there. So look, we have 2 bonds. This is called a double bond. Yes, we can have double bonds. So a double bond consists of 1, 2, 3, 4 electrons shared between 2 atoms. So let's check our octet rule now. Let's look at this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Still has 8 because we just took these 2 and moved them here to share them with the carbon. Let's look at the carbon. 2, 4, 6, 8. Oh, that looks good. But how about this oxygen? 2, 4, 6. This oxygen only has 6. It needs 8. So what are we going to do? How about we take these 2 and create another double bond on the other side? So let's get rid of these. And I'm just going to move them over to create a double bond on the other side. There we go. There is another double bond. So let's check it out. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8. It's good. Carbon, 2, 4, 6, 8. It's good. Oxygen, 2, 4, 6, 8. We're done. This is the structure for carbon dioxide. We used up all 16 valence electrons. Everything satisfies the octet rule. That's all there is to it. All right, here's another example. Here we have diatomic nitrogen, 2 nitrogens that are going to be stuck together. So first of all, we need to count up our total valence electrons. We only have nitrogen, but there's 2 of them. Nitrogens have 5 valence electrons for a total of 10. 10 total. So we have to use all 10. Have to. That's one of the rules. That's what atoms do. So let's take these nitrogens, and the only thing we can do is put them next to each other. There's 2 of them. What else are you going to do? There is no central atom. They're just going to be stuck together. All right? So we use 2 for a single bond. We need to use 10. So let's put in the other 8. So there's 2, 4, 6, 8, 10. There's our 10. We used them all up. Now we can't add more. We can't take any away. We're done with that. Now we have to check to see if each atom, each of these nitrogens, satisfies the octet rule. So let's check it out. Let's look at this nitrogen. 2, 4, 6, 8. That one's good. How about this nitrogen? Only 4. 2, 4. We got to fix that. So I hope you're thinking maybe a double bond again. So let's take 2 away and see how that works out. Let's take these 2 out and create we'll move those over to here. Okay. All right, so now what do we have? Let's look at this nitrogen. 2, 4, 6, 8. That one's still good. How about this one? 2, 4, 6. Getting better. So what do you think? Let's move 2 more electrons around and see what happens. Let's take these 2. And now we're going to move them over here to create a triple. We can have triple bonds. I know, you're probably very excited about that. I am too. Triple bonds. We can do doubles, we can do triples, but that's it. There is no quadruple bond. It stops at triple. So I hope that makes you happy. So let's check it out. Nitrogen, 2, 4, 6, 8. This one has 8. How about this nitrogen? 2, 4, 6, 8. And it's okay if they're down here. Technically, they'd probably be on the side. You don't really have to move them, but I'm just going to move them. I like to have things symmetrical. 2, 4, 6, 8. Done. Octet rule. We used all 10 electrons. This is our structure for N2. There we go. Let's look at something called hydrocarbons. You're going to run across these. They're not very difficult to do the dots, but there's a couple things I want to point out. Hydrocarbons are when you have these carbons, more than one carbons, what they end up doing is they like to stick together and make these long carbon chains. Polymers and carbohydrates and proteins, a lot of things are these long carbon chains. You could have carbon chains of hundreds and even thousands of atoms long for really big polymers. But we're just going to do some small ones. So whenever you see carbons, you're going to want to stick those together. All right. Now we have 4 H's we have to deal with. So let's just do 2 on each of them. We'll put one there, one there. Again, molecules like to be symmetrical. Okay, it's attached to the carbon. So we have C2H4. All right, everything's nice and symmetrical. Let's get an electron count before we go any further. We have carbon, there's 2 of them. They have 4 valence electrons, that's 8. We have hydrogen, there's 4 of them. They each have 1 valence electron, that's 4. So we have 12 total that we have to deal with. All right, so we stuck them together. Let's see, we got 2, 4, 6, 8, 10. We need 2 more somewhere. I don't know, where we're going to put them. What do you think? Before we put them down, let's think about this. Your hydrogens are good. Once your hydrogens are attached to something, don't mess with them. Don't put dots on them. Don't put double bonds or triple bonds because that's too much. They can only have 2, so once they're attached, they're done. Let's look at these carbons. This one here, 2, 4, 6. Not enough. How about this carbon? 2, 4, 6. Also not enough. All right, we need to get 8 on these carbons. We can't mess with these hydrogens. We have 2 more we have to put in because we're only used up 10 here. We only used up 10, 2, 4, 6, 8, 10. So 2 more, how about here as a double bond? So now we use 2, 4, 6, 8, 10, 12. We used all 12. And let's check the octet rule. This carbon, 2, 4, 6, 8. This carbon, 2, 4, 6, 8. We're done. There's the structure for C2H4. All right, here's another example of a hydrocarbon, but this one's a little different. It looks kind of long. We have this OH hanging out on the end, so how the heck are we going to put this together? The way this is written is going to give you a clue to what the structure should look like. This is kind of what organic chemistry is about. Organic chemists like to write formulas that represent what their structure is going to look like. So we're going to have a CH3, a CH2, and an OH. We're going to lay it out just like that. And remember, we're going to attach these carbons. Even though they're not on top of each other and they're kind of spread out, they're still going to be attached. So we have a carbon attached to another carbon. All right, so we have a CH3, so that means this first C is going to have 3 H's on it. There's one, there's another one, there's another one. You see how this is CH3? Then we have CH2, so we're going to put 2 hydrogens on here, and I'm going to write it like this because with this OH on the end, it literally goes on the end, just like it's written, OH. So you see how this is CH3, CH2, OH. This is giving you a clue to the structure, so we're going to write it just like that. We need to get an electron count because there might be some missing here. So how many carbons do we have total? There's 2. They each have 4 valence electrons. That's 8. How many hydrogens do we have here? Let's not make sure we get them all in. 3 and 2 is 5, and 1 is 6. So we have 6 hydrogens. They each have 1 valence electron, so that's 6. And we have 1 oxygen, and oxygens have 6. So let's add this up. What's 8 plus 6 plus 6? Should be 20. So we have 20 total that we have to use. Let's see how many we used up just putting this together. 2, 4, 6, 8, 10, 12, 14, 16. We use 16. We need 20, so we have 4 more. We need 4 more to put someplace. Where are we going to put them? Again, don't mess with the hydrogens. Once they're attached, you can't do anything with them. It'll mess them up. They only get the 2 from the bond, and that's it. Don't put them on there. How about these carbons? Let's look at this one. 2, 4, 6, 8. This one's good. How about this one? 2, 4, 6, 8. This one's good. How about this oxygen? 2, 4. That's a problem. It needs to have 8. But guess what? We have 4 that we need to put in someplace. So let's put them in as unshared pairs right on that oxygen. So now this oxygen has 2, 4, 6, 8. We used up all these. We used up the 20. Everything satisfies the octet rule. This is our structure for CH3, CH2, OH. This is technically an alcohol. And when you take organic chemistry in college, or if you take AP Chem, you'll talk about alcohols, and usually things with OHs hanging off the end are alcohols. All right, lastly, we're going to talk about polyatomic ions and write the structures for those. So we're going to do it the exact same way. The only way these are different is we have to account for the charges on these things. This is the reason why these polyatomic ions have these negative charges or sometimes positive. So same process. Let's do this. We have one phosphorus. Phosphorus has 5 valence electrons. That's 5 total. We have 4 oxygens. Oxygen have 6 valence electrons, 4. And now this -3, if something has a -3 charge, that means it has 3 extra electrons because electrons are negative particles. So if we have 3 more electrons, we have to add those in. We're going to add in those 3. So now what do we have? We have 24 plus 5 plus 3. There we go. We have 32 total. That's a lot of electrons we have to use up, but we can do it. Let's note something here. Have you noticed that all these total numbers have been even numbers? Yeah, there's a reason for that. We need to have even numbers for everything to share things properly. This is why this PO4 ends up picking up 3 electrons. Let's see how that's going to work out. So we're going to put our single atom in the middle. Phosphorus is all by itself. And then we're going to put these oxygens around it nice and symmetrically. Okay, then we're going to attach them one time to the phosphorus, to the central. All right, we're going to start there. So we used up 2, 4, 6, 8 just binding the oxygens to the phosphorus. But we need 32. What are we going to do? Where are we going to put them? Well, the phosphorus already has 8 from all the bonds, 2, 4, 6, 8. Look at these oxygens. They only have 2, the ones that are attached to the middle there. So we're going to start putting all these other electrons around the oxygens. So we have 2, 4, 6, 8. Let's pick it up from there. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We used all 32. Let's check out the octet rule. We already know phosphorus was good. How about these oxygens? 2, 4, 6, 8. How about that? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Octet is satisfied. We used all electrons. We're done. This is the structure of a phosphate polyatomic ion. So you can see why we needed this -3 charge. If we were missing 3 electrons, this would be difficult. This wouldn't really work out. All right, let's check out another one here. This is SO3 -2 sulfite. So let's get a count before we start doing anything because this could get hairy. We have 1 sulfur. Sulfur has 6. We have 3 oxygens. Oxygens also have 6. And now we have a -2 charge. So don't forget that. We have to add the 2 in there or else it's not going to work out. So we add these up and we have 26. 26 total. So we have to use all 26. So let's start laying them out. The sulfur goes in the middle. We have 3 oxygens. I'm just going to put them around like this. It's pretty good. Attach them once to the middle. Always start with just a single bond because who knows if we need doubles or singles or what. So there we go. They're all attached. What do we have here? 2, 4, 6 that we used up. We've got to use up 26. So let's start putting them around. Let's just start putting them around the oxygens and see how it works out. We can move them later. Not a problem. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Where am I going to put the other 2? Because look what happens. These oxygens are good. They all have 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But look at the sulfur. Sulfur only has the 6. So we have 2 more that we have to add to get up to 26. This is only 24. There's 25 and 26. We'll put them right there. We'll have an unshared pair on the sulfur. 2, 4, 6, 8 satisfies the octet. These satisfies the octet. We're good. This is the structure for a sulfite ion. Let's just look at an SO3 molecule, not a polyatomic. See how it's kind of a little bit different than the one we just did. This one doesn't have a charge on it, but let's check it out. We have a sulfur, one sulfur, sulfurs are 6. We have 3 oxygens, also 6, 18. This time it adds up to 24. Before we had 26. Now we have 24 total. All right, let's lay it out. Similarly, how we just did the other one. Okay, 3 oxygens, 1 time to the middle. Okay, we used up 2, 4, 6. We got to get to 24. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, we used up 24. But you can see now the sulfur is missing a pair. Or it's missing 2 somehow. It only has 6. 2, 4, 6. The oxygens are good. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Somehow we got to make this sulfur happy. We got to get it 2 electrons. So we can't add 2 more electrons because we can't just pull them out of thin air. We have to use the 24 that we started with. What are we going to do? How about moving a couple? Let's get rid of these 2 and simply move them to create a double bond, just like we did before. So now by doing that, it shares 2 more with the sulfur. So the sulfur now has 2, 4, 6, 8. It's happy, has the octet, its octet satisfied. And it didn't mess up this oxygen. 2, 4, 6, 8. The oxygen is good. It has its 8. Everyone has 8. We're done. There's the formula for sulfur trioxide. Let's look at this polyatomic that has a positive charge. We haven't done those yet. So we're just going to do the same thing as we've been doing. We have 1 nitrogen. Let's get an electron count here. It has 5 valence electrons. We have 4 hydrogens. They each have 1, so that's 4. If this is a positive 1 charge, what does that mean? We're missing an electron. So we have to subtract 1 this time around. We're going to subtract. A positive means it gave away an electron, so it's missing 1. So we have to get rid of it. So this is going to add up to 8. See why we need this charge here? If this -1 wasn't there, 5 plus 4 would be 9. You can't have odd numbers. Remember that. You always have to have an even number for your total. So this is why this carries a positive charge. So let's lay it out. We have nitrogen in the middle. We have 4 hydrogens. We'll put them symmetrically around the nitrogen. We'll attach them each once with a single bond. Let's see how many electrons we used. 2, 4, 6, 8. Oh, good. We used up all 8. Let's check the octet rule. We know hydrogens only get 2, so they're done. Look at the nitrogen, 2, 4, 6, 8. We're done. This is the formula. This is the structure for ammonium. That's what NH4 positive 1 is. So there you go. That's how we write Lewis dot structures for covalent compounds.